Let's start with the definition of the linear momentum. For a particle with mass m moving with the velocity v, we define the linear momentum of this particle as p equal to mv. This is the definition of the linear momentum. In Newton's time, this quantity was called the quantity of motion. The quantity of motion. From this definition of the linear momentum, you can see that the momentum of a particle gives us the idea of how hard to change the motion of a particle. If a particle has large m, or it has a large velocity v, in both cases you can see that it is hard to change the cause of motion. So it means that if you have the large product of m and v, it is hard to change the cause of motion. This can come from the large m or large v or both. So we call this a quantity of motion. That is, it gives us the idea how hard if we want to change the cause of the motion. We can see this also from the Newton's second law. That is, if we start from F equal to ma, we can also write this as m dv by dt. Okay, and if we assume that the mass m is a constant, so we have that F is equal to the d by dt of mv, which is equal to the dp by dt from the definition of the linear momentum. From this equation, you can see that if you want to have the large rate of change, or if you want to change a large amount of the momentum in a short time interval, you need the large force. Okay, you can see that this dp by dt is the rate of change of the momentum So it means that if this is large, it means that you want to change the large amount of P, or you want to change whatever the amount of P, but in very short time, you need a large force. So this gives the idea of how hard to change the course of the motion. It means that if you want to change the course of the motion rapidly, you need a large force. So the large force means hard. It is interesting that this form of second law, F equal to the dP by dt, is the form that Newton used in his time. It means that he gives the second law in terms of the change of the quantity of motion. But we know that P is equal to mv, and if m is a constant, we can move this m out of the derivative and get this relation, and dv by dt is a. So we have F equal to ma, as most of you are familiar. But the more general this relation is more general. It's more general form of second law. We can use this form to the system that the mass is not constant. You can see that mass is inside the derivative, so it's not necessarily constant here. So we can use this to the system with varying mass, which is the problem that we will discuss in the last section on the log-get proportion. It is also interesting that if you study in the advanced course of physics, like if you study the relativity theory, this form of force is valid. When the particle moves very fast, the velocity is close to the velocity of the speed of the particle is close to the speed of light. We cannot use this form of second law, but we can use this form of second law in that case. So that is why I say that this is the general form of second law.